Hello everyone, welcome to the eighth lecture of our course. And in this lecture, we are going to learn about numerical computation and how to do it using Julia. So, in all the previous lectures, we have learned about the basics and intermediate stuff, and that has equipped us with enough knowledge and arsenal to tackle these numerical computation problems. Okay, so what is numerical computation? This is a method of solving mathematical problems, different real life problems, which can be represented with mathematical equations using numbers. So we are used to solve problems with symbols, with exact methods, but here in numerical computations, we are going to use numbers and approximations to solve these problems using several algorithms. And our goal will not be to find exact solutions because in some cases it is not even possible to get exact solutions. So our goal will be to find approximate solutions that are good enough to work in real life. So that is our goal for today's lecture, and that represents the essence of numerical computation. So why are they necessary? Let me type it out so that it remains in the notebook. The first thing that we discuss is that exact solutions are oftentimes impossible to obtain in real-world problems because the problems become more complicated. There are many equations, many nonlinearities, many variables that will be too much to solve for a human inverse. So, in those cases, numerical computation can be of great aid. Sometimes the data that we obtain is too big to be comprehended by us, and we need the help of computers and numerical algorithms to represent and analyze this data, as we have seen in some examples in the previous class. Sometimes the models that we are using are too intricate and messy to work with symbolic math. Sometimes our systems are nonlinear to such a degree that it is not possible to solve them. So, in all these cases, they need numerical solutions. And the obvious thing is computers are fast, so we can approximate things fast and make it accurate enough to use in practical situations. Okay, so these are some of the most important reasons why numerical computation is necessary. Okay, so let me quickly show you a presentation that I also made for today's class. So we have discussed what numerical computation is. So essentially, it is crunching numbers and going beyond the symbolic math that we have known so far. And the main motivation behind doing this is that the data that we collect in real world is always in the forms of numbers. And we have to have some techniques to use those numbers to advance our analysis. And that is the essence of doing numerical computation, and it is being done long before computers were available. Okay, so it has been translated, it has been changed, it has been remastered to get adapted with our modern technologies, but the methods still stand, and we'll be learning about them in this course. So there are mainly three different kinds of numerical computation that you are going to encounter. First is interpolation, then integration, differentiations. And using these three, you will be able to tackle most of the problems. So in today's lecture, I mainly plan to introduce you to interpolation, what that is, and how you can do that. So if time permits, I will also wanna introduce you to numerical differentiation. So what those are, we will gonna be seeing in the next few slides, and we are also gonna be doing those live coding sessions. So we start from the scratch. We learn the concepts, the theory, and we'll also write some code. And after that, I will also going to introduce you to some packages that are developed in Julia to help us use these methods more efficiently.
Okay, so what can you solve numerically? We can do interpolations, we can do differentiations, we can also do integrations. So let me go and talk about them very briefly. So interpolations are basically estimating something from known data. Suppose you are taking some data points. Okay. So to give you an example, suppose you are collecting data from an experiment and X is your independent value and Y is your actual data. So suppose you have collected say 10 data points, and now after collecting data, you are seeing that you have forgotten to take data at a particular point which you needed. Now what you have to do, you have to guess a value there, or you have to redo the experiments. If it is impossible for you to repeat the experiments, then you have no other choice left other than guessing the data at that particular point. So that's what interpolation is actually doing. It is estimating some values with the help of your known values. Okay, so it has different algorithms, different estimation methods, and those are different interpolation techniques that we're going to learn today. So, and what are differentiations? This represents the rate of change of some variables. Similarly, integrations are used for finding the sum or area under a curve. Okay, so these are the things that we're going to learn in numerical computation. And in the last lecture, we will see that how we can use all of this knowledge to solve ordinary differential equations. Okay, so our first topic today is interpolations. So let me quickly make a heading and then we So let us go to the presentation again and let us see what interpolation methods are available to us and how we can implement this in Julia. Okay, so yeah, so this is what I was talking about. This is interpolation, which is basically estimating a value. So suppose this is our data that we have collected. One is x, which is collected at 0, 1, 2, 3, 4, 5, 6, these 7 points. And this is the function that we are trying to get a estimation of. So here we have only 7 points. So if you plot them, these are going to look like this. So suppose we ask the question, what will be the value of 8.5? So if you look at the data collected, you will see that there is no value that is known to us from real experiments at x equal to 2.5. So what we can do, we can estimate the value. And one way of estimating this will be to connect the closest two values, which will be serving as a upper and lower bound, and connecting those two with a straight line, and say that the value that is falling on the straight line at that particular point will be the value. So this is one of the interpolation method. This is called linear interpolation. So before learning about that, we are going to learn about nearest neighbor interpolation, then we'll learn about linear interpolation, then we'll move on to polynomial and span. Okay, these are different kinds of interpolation methods. So some of them are useful in some cases, some of them are useful in a different scenario. Okay, so I will try to write the codes for the nearest neighbor interpolation and also for linear interpolation from scratch, and we'll see how we can use the other two with package. Okay, so let us jump back to our notebook, and we are gonna learn about nearest neighbor interpolation first. So what is this? As we were discussing here, your unknown value that is to be found is at x equal to 0.5. So instead of doing this, joining closest two points with a straight line, what you can do is you can see which of these values, the collected values, are closest to our one that we are trying to find. And we will assign the fx value of that closest point. So that is nearest neighbor interpolation. So we will get our unknown data point where we are trying to find the value of fx. We see the closest data point of x which we have collected, which one is the closest to our unknown point, and we say that the value of this closest one will be our interpolated value or new estimation. So here you can see why this can be a tricky situation, because x equal to 2.5, this is midway between x equal to 2 and 3, and we don't know which one to choose. So let me quickly check these values. So this is our x, and our y is actually sin x. You can check the values. These are 0, 0.84, 0.90. Let's see. So these values that are listed here are an approximation for a sine function. So let us plot it. So before plotting, you know that we have to use the package plots. Let us also do UI, and let us start from here. So we'll wait a couple of seconds for this package to get installed. So the packages are installed. So let us quickly define our backend, which will be the GR backend, and also define the size of our plot. So let us do 400 by 0. Okay. So what we're going to plot is X and Y, and we are going to use the scatter series time. So you can see that this already is following a sine like trend, but again we want the value at x equal to 2.5. So define the x level, and y level. So we want the value at x equal to 2.5. So let me plot that also. With the lines command. So this is the point where we want to know the value of this y. So we will first start with nearest neighbor interpolation, and we see how we can use that to get an estimation of this y value. So this will find the value of x for which y is known. So in our case, this will find from the range 0 to 6, which is closest to our unknown x. So let me also define a variable x unknown, and let us say that it is 2.5, and then plotting a vertical line at x unknown. Okay, so let us implement this nearest neighbor interpolation using a function. So let's call it nearest neighbor interpolation, and it will take 3 arguments. We have to provide it the known x, known y, and then unknown x. So let us call it x unknown. Okay, so I am not specifying what the data types will be of these 3 variables, but we'll assume here that known x and known y are arrays, and is just a number. Okay, so let me quickly write down the steps that we're going to follow, and then I'll write the codes for those steps. So first will be to find the value from known x, which is closest to x unknown. Okay, and then assign and return y unknown is equal to value of known y for, so let us call this x closest So we are going to return the value of known y for x closest. So let us say that this will be our return value. Okay, so how can we get the closest value of a known x? So we can check. Let me write the code here for demo first. So suppose our array is 1 to 10 and we want to find the closest value from this array at, say, x equal to 5.8. Subtract this number from our array, and this will say that this is not defined because I have mistyped it. And you see that this is our current array now. So let me do one thing. Let me make it yeah. So these are our elements. So from these, the one that is closest to 0 will be the value of known x, which is closest to our unknown point. So how you can get that? We can sort all these numbers in ascending order, and then the first value is gonna be the value which is closest. But if you just use the sort function, you will see that this is returning the same thing. So what this sort function is, you can go to the light box and check that if you give it a array, this will return the elements sorted in ascending order. So here you can see that this is not doing our job because some numbers are negative and some numbers are positive. So here you actually want to get this value 0.2. So this is what we have obtained after subtracting the element from our known array of x, which is test x here. So what you can do is you can get the absolute value of all these numbers, and you can do that using the APS function. And again, we want to broadcast it, so we are gonna use this APS dot. And now if you run it, you will see that this is returning 0.2, which is the minimum distance of these elements from 5.8. But again, we don't want the minimum distance. What we want is the point which is at minimum distance. So what you can do is get the first element from here and add it to 5.8 because we are subtracting here. So that will give you the value of x which is closest to our given data point that is unknown. So that is one of the way that you can do it.
Okay, so another way will be to use the short form function. So instead of giving you the sorted array, this is going to give you the index of the array elements in such a way that if you uh, go through the index, this will give you the sorted array. So you can go at live docs and look at sort form. So this returns the permutation of vector or array I that puts AI in sorted order along the given dimension. Okay. So if it is a 1D array, then the dim's keyword argument must be split. Okay. So if this is not 1D, then you must specify the keyword argument, otherwise it is unnecessary, as we have seen in other cases also. So what this will do is, so let me again type this out. Okay, so here we are getting this array, and if we use the sort form function on this, then we will get this array. What this means is that the sixth element is the smallest, then fifth element is the second smallest. So what we will have is this. If we use this short form array on this expression, and then we use the result of that evaluation to index into this expression, then the result that we are going to get will be similar to this. Okay, I have removed that actually, so let me write it out here also. Okay, so this two result will be similar, so we can just check. We see that this will be similar. So what is the advantage of using that? If you are using this, then we can simply get the closest index instead of the closest number as we are getting here, which is 6.0. So when you have the closest index, you can use this to index into our known data arrays, and that will help us in getting both closest x and y, this known y corresponding to the closest x value. Okay, so I'm going to show you this directly in the function. So let me fold those things. So we have the space. So here we need to find the element which is closest to our unknown value. And instead of finding the element, we are going to find the index of the element in this known array, which is closest to our unknown value. So here test x will be our known x, and this will be our x unknown. So what will be our closest x? That will be known x, closest index, and our y unknown is going to be known y, closest index. So let us return both the closest x and y unknown so that we can compare that it is getting both of those values correctly. So this is our function. So let us plot this. Okay, so this cell here has been disabled, so it doesn't matter. So what we want to do is call the function that we have just written. Okay, so this is going to return us the closest x and the y unknown. Okay, so this is not properly written, so it will not run. But okay, so our known x here is x and known y here is y. Okay, there is something error happening. Let me quickly check it. Okay, so we have misspelled it here, here, here. Now it is correct, and this should also disappear. No, another spelling mistake here, and everything should run. Yeah. So here the output, these two values you can see here, but for clarity, let me print it out. And let me also call the plot function with this exclamation version so that we get to see the plot also. And too many spelling mistakes here, and we need to put a. So first, let us get the example 2 point at x equal to 2.1. So here you can clearly see the closest point is this point, which is x equal to 2, which was our known data. So it should return this value x equal to 2, the first thing, the closest x, and then the y unknown should be the value associated to this known data point. Okay, so we can check that it is returning that the closest x is 2 and 0.9093 is going to be the value or our estimation through this interpolation method. So you can check the y values and you see that at 0, 1, 2, this is the value that is equal to our estimation. So our function is working as expected, but we will see each case when this happens. So this point is exactly at the middle between this x equal to 2 and x equal to 3 point. So in those cases, you can choose what to do. So you have to choose either of these points. So you can make a convention to choose the lower values or the higher values, but that is up to you. And here, since we will always be getting this first index, so we can probably check it from here also. So let me call it test. Unknown is 5.8 and this should be 5.8. This should be 5.8. This, this, this should be 5.8 and this also. So let me save it and yeah. So you can see that this value is 6, which is the index. So what's gonna happen if we take the unknown value to be 5.5? You'll see that there are 2 points which are coming out to be zero point 0.5. So where the difference is coming out to be zero point 0.5. And in this case, since we are just referencing the first array element, then it is always going to be the values which is stored toward the beginning of the array. Okay, so that is because of the algorithm that is being used to sort the array. So we can confirm this from here. You can check through this absolute value of the differences that there are two values of 0.5 and if you use the short form function, you will see that the lower index will be at first position. So it is essentially saying that the fifth element, which is 1, 2, 3, 4, fifth, which here is 5, is closest. Again, you can invert this definition and choose this one also. So the way we have written this function, it will always use the lower of the values when we are getting two values which are equally spaced from the unknown point. Okay, so I think that has cleared this edge case. So now let us do this for all the points in this range. Okay, so how can I do this? Let me again plot everything here and again this is going to be disabled after I run it. Okay, so what I'm gonna do is disable this cell and run it. Okay, so here our x unknown, it can be a range also. Say I want at 2.5, 2.2, 2.3, and when you are giving it a array, it will not work. So we have to change the definition of this function slightly. So here it is. So here, if you use broadcasting method. This will again give you an error because there are other arrays also. See, it will give you a dimension mismatch. So what is happening here is that when you use the broadcasting method, this will treat these expressions and this expression, everything, it will treat as if it is broadcasting. So what we can do here is that we can say, we can omit the type checking for now. So we can say that there will be empty array for storing the closest index, closest x value, and the y unknown values. Okay. So for clarity, let me call it unknowns so that it is signifying that we have multiple elements here. So what we can do is put a for loop here and complete it. So here I will index this element like this, and we can put everything in this array. Okay, so that is gonna work. I just have to make sure that every variable name change has been accounted for. So if I run it and remove it, it should work. No. Okay, okay. So there is a small mistake here, that is these are empty arrays, but I am trying to reference them. So we can easily fix that by defining a zeros array with all elements zeros, with the size being equal to that of our x unknowns. And here, let me quickly check if everything seems okay. Okay, another thing is that this is now not defined. So this just will be the value that we have stored in there. So here, okay. So here, since we have the error that we are getting is saying that we cannot use a float to index into arrays, and that is happening because, where did it go? Yeah. So we have said that this is going to be a array where all the elements are zeros, and since we haven't specified any data type here, everything is going to be a float. And so when we are using this array to index into our known arrays, that is giving it as an error. I'm sure you guys already figured that out. So let me give it a type, and then here we can see that this is running. So these three lines are representing the unknown data points. But let us plot our estimated points also, the different color, say maybe dark red, and you can see that these are the points which has been estimated. So let me show you the print message also. So here you can see that the first point, 2.5, although it was equidistant from both x equal to 2 and 3 points, since we are choosing the lower of the values, then this is going to be choosing this value of x, and the corresponding y value was this. So this will be plotted along this line. Similarly, x 2.2 and 2.3 both had the closest value to be 2. If we just add one element at 3.1, you will see that it will choose the closest value to be this one, and the estimation will be here. Okay, so let me just fade the vertical lines and use dot to represent them, or maybe dash, yeah, to represent them that these are the unknown points. Okay, so now what one can also do is that they can look at the whole range and just plot everything. Okay, so let me copy this, paste this. So everything here, I will append the 2 so that we don't run into those variable issues. I forgot here and here. Yeah, so it is still running, and I'll just change one color so that we are not confusing it with the previous plot. So what I want to do is I want to look at the whole range where our data is defined, and I want to get an estimation from all the points in between. So our range is 0 to 6. So let me say that we want to get estimation for all the data from 0 to 6 at intervals of 0.1. Okay, so if we run it, we can stop this print statement. If we run it, you will see that it is not at all properly visible. So we'll stop this also, and you'll see that the estimated values will look like this. Okay, so up to this point, the closest value which was known to us was x equal to 0. So everything was assigned the y value corresponding to x equal to 0. Same for this point also. So we can make it a line plot and remove the marker so that it looks good. So you can see that this is the overall estimation. So as those who have already seen how a sine function looks, they can easily say that this is not at all a good estimation. So when is this useful? Mainly in two cases. One is, so let me rerun this again. So this will be useful when the x and y values are not so far apart. Okay. So let me quickly define x3 and y3. Say this is 0.16, and this is again sine of x, x to y2, and here it is also going to be x to y2, and we have, so this is 2, okay. So here you can see that this is our plot. So suppose this has already enough data points. So suppose we want to get data at a location, say 0.55, which is again not in our data set. We have 0.5, but not to it up to the second decimal point. So if you run it and say this is a scatter, you see that this is choosing this point. So this is one of the cases when this is very useful, where you have already enough data points, but you want some missing data and that kind of thing. Okay. So another use case will be to uh, estimate values when we are doing multi-dimensional operation. Okay. So suppose we are working with a 10D array or 15D array, and then doing the other methods, the linear interpolation or spline interpolation, those can be very computationally heavy and time consuming. So in that case, this method, this simple method can be used very effectively. So these are the main two use cases, but for 1D arrays, we will generally not use this nearest neighbor interpolation because in general, we can see that this will not give you a good result. So what we're going to use is the linear interpolation. So let us see how we can do that. Okay, so what is linear interpolation? Let us go back to the presentation. So in linear interpolation, the unknown values are obtained from a straight line approximation. So you can take the above example, above meaning the one that I discussed here. So here the unknown point was at x equal to 2.5. I wanted to know what the value will be at x equal to 2.5. So in linear interpolation, in the above example, we can use this fact that 2.5 is midway between 2 and 3, and it is then reasonable to take that the function value of the function at 2.5 will be midway between f at 2 and f at 3. So this is generally adding a straight line, imagining a straight line between the points 2f2 and 3f3, and on that straight line, it is saying that the value of the unknown points will lie. So in general, this linear interpolation takes two data points, this xayA and xbyb. Those are the bounds, and the approximated value will lie on the line which is connecting these two points, and this will only give us the value between the range xa and xb. So if we see here, so here we were interested to obtain the value at x equal to 2.5. So the 2.5 we have these bounds x equal to 2 and x equal to 3. So this point here is 2 f2. This point here is 3 f3, and we have drawn a straight line there. Now the value of x equal to 2.5 following on that straight line. So where the straight line and the vertical line x equal to 2.5 will be intersecting, that will be the estimated value of our function at x equal to 2.5. I hope I have made it clear. So let us go to our notebook and see how we can implement this. Okay, so let us see how we can implement this linear interpolation in code. So we will be using a function for this task. Let me call the function linear interpolation. So this will take three arguments. The first will be the array of known x, then the array of known y, and the third one will be the array which will contain all the unknown points that we want to estimate a value for y. Okay, so we will need a for loop to iterate over all the data points, unknown data points. Then we also need a return statement, and let me initialize our y unknowns with all zeros. So in this array, we will be storing all the estimated values. Okay, so that's what we are going to return. Okay, so now let us create the for loop, and here we will have two steps. Okay, the first will be to get the bounds of the straight line. So this essentially is getting the two closest points, xa and xb, in such a way that our x unknown belongs to this interval. Okay, so this is the condition that we want to make sure is true for all the values of this unknowns. Okay, so when we have this, then we can join these two points using a straight line. So we get the equation of the straight line that is passing through the points xa, ya and xb, yb, and our assumption is that the value of y unknown, when this condition is true, will lie on the straight line that we just created. So x unknown, y unknown will be a point on this straight line. That is our assumption. And how good that is, we are going to see when we complete this function and do the plots. Okay. So here y unknown can easily be obtained from the equation of the straight line. Okay, and the equation is given here. This is this one. So this says that the interpolation takes two data points, these xa, ya, xb, yb, and the approximate values between the xa and yb intervals will be approximated with the straight line. And the equation of the straight line is given by this y equal to ya plus yb minus ya multiplied by xa minus xa whole thing divided by xb minus xa. So you can check whether the equation of the straight line, which is passing from these 2 points, is actually this one. You can do it using simple coordinate geometry, but for this lecture, I am going to skip it. This is a homework task, and I will use this function directly in the code. Okay, so let us do all these steps one by one. So first is to get the bounds. So we can do this by separating all the points that are greater than our unknown value. So let us call it x unknown, which will be the ith element of this x unknowns array. Okay, so here we are getting the value of unknown x. Now we look at all the points that are below this or less than this, and all the points that are greater than this. So we can check. So we can check from here that in order to get these two boundary points, what do we have to do? We can, so suppose this is our, just wait a moment. Suppose this mark is actually our x unknown point. Okay. So what we can do is we can look at all the points which are lesser than this, and then the greatest of them will give you one of the bound. Then similarly, we can look at all the points which are greater than this unknown point, and the lowest of them will give you another value. Okay, so that's how we can get two of these bounds that is going to create our straight line. So let us come here. So just a quick heads up that this way of finding the bounds will only work if we have sorted our data. Okay, if we have not sorted, we can still do it, but this will be uh, 3 lines of extra code for every iteration. So we want to avoid that. So we should sort our data with independent value in a ascending order. Okay, so we can do it like this. Sorry, this is going to be a third bracket. So this is just sorting. And I will not be explaining all the functions and all the array indexing again because we have already seen this in the previous lectures. So with that out of the way, let us get the lower bound. So here we will look at all the numbers which are smaller than our unknown. So you can do that like this, or we can just do it like this also. So we have to check which of the numbers in the array after evaluating this expression is less than 0. So we can simply use it like this, say less than and equal to 0. So we wanted to check this, but we can just take this no next array to the right hand side, and this gives us a simpler expression. And what we can do now is we can use these true false values to index into this array, and this will just give us the elements which are smaller than this x unknown. So suppose now we want to get the xa, the one of the bounds. We can do that like this. So this will be the last value of that array. Similarly, we can get ya also like this. Okay. Now we want to get the upper bound. So here we want to check all the elements which are greater than our unknown value. So how can I do that? Okay. So I think I have typed it oppositely, although it would not have mattered because we are anyway getting the two bounds here, and the straight line is unique between the two bounds. but just for consistency. So this will give us all the bigger points. Now our XB is going to be the first value of this X figure array. Similarly, we can also get YB like this. So what I will do before proceeding to get this equation and get the unknown value, I will for now return the arrays XA, XB, and YA, YB. So what this will help us is that we can plot them and we can see whether the bounds that we're getting is actually correct. Okay, so let me quickly plot something. So we had x2, y2. So their points are two lanes. Let's just plot x and y. Okay, and then we get x bounds and y bounds. If we run the function linear interpolation, we will pass x and y here, and our unknown is say 2.5. And it is giving us error. Let me quickly see. Okay, so here the problem is that this is a number and this is an array. So what one can do is simply say that this will be doing element-wise operation. Okay, and while I am here, I think I have spotted another error. This one. So this will be small x underscore b. And let's run it. And it is giving another error. It is saying that x underscore a is not defined. Okay, so what is happening is that we are defining these values inside the for loop, and after the for loop has ended, these values are out of scope and the function cannot access them. So what we can do simply to fix this error is that we can make an array of these. So this will again be initialized with all zeros, and then let me quickly do them for xp, ya, and yb also. And now what we can do here is that instead of storing in these variables, we can store them in this array that we created itself. Okay. So similarly here also. Okay. So now we don't have to return all of them and create the array here. We are already creating the array. So we can just return those. Okay, so this will give another error because these are array and everything should be in place. Actually, we can also concatenate them horizontally so that it will be a bit easier for us to do the plotting. So you will see that this is our result of this function linear interpolation, and here you can check that this is giving you a matrix 1 plus 2 matrix 1 because we have only one unknown data point, and 2 because one of them is representing the lower bound and another of them is representing the upper bound. So these 2 points is the lower bound, this is the upper bound, and these are the x values and these are the y values. So what you can do is you can just plot the x bounds and y bounds. Let me also do it scatter plot, and let me say that the color will be different for them. So let us do red and green. So like this, yeah. So here you can see that our unknown point is 2.5, which is here. So let me add a gray lines also. Here, and you see that the lower bound and upper bound, so which will create the straight line, has been obtained correctly. Okay, so the function that we have written so far to obtain the bounds of the straight line is working. So let me just the equation that we had. This one to get the y unknown also. So let me say we will directly store it in the array. This is going to be so ya, which is our ya array at that particular point. Then we have these three that we have to consider. So we have yb array minus ya array xb array minus xa array and then this x unknown minus xa array. And we will also return the y unknowns. So let me call it y unknowns. Okay, this is going to be this, and we're getting answer. For now, we can check whether this is correct by taking the average of these 2 points. So 0.90, 0.1411, and you can see that this is very close. So our function is working as we expected. So we will stop plotting the bounds and we will rather plot the x unknowns and y unknowns with a certain color, and let's make the marker size a bit smaller. Okay, so we have to define these as x unknowns. This also should be this. So here you can see that the point that we're obtaining is lying on this particular value of x equal to 2.5, and one can also check that this is just falling on the straight line which is obtained by joining the closest 2 points. Okay, so we can just draw the straight line using this xy array and yb array. Those, as we are giving those are data points, we can join the straight lines, but we have a better way of checking that. So let me copy everything to a new cell, and let's say that we are plotting this number. Okay, and make it pale green so that the visual difference is there. This has to be y knows 2. Okay, so this is our point. Now let's say that we want all the points from 2.1 to 2.9, which will be in between these 2 points, and we want them in the spacing of 0.01. Now, if we run this, then we should get a straight line here. Why? Because every point that we're going to be getting here will have the same two closest points of known data points, and the straight line getting joined by those two known data points will be this one, always this one. And then if we are getting the x unknown value from this array, which is again within this range, then and the y unknown is falling on this straight line, then if we just plot the y unknown estimation and x unknown value, we will essentially get the straight line. Okay, so before granulating it like this, let me do it for a smaller interval, and you'll see that every point is falling on the straight line connecting these two. Similarly, we can do it like this, and you will see that this is exactly doing what we are expected to do. So we can say that we want from 0 to 6, and you will see that this will get the estimation by joining the lines of this pair of known data points. And for each unknown point, it is going to choose a suitable set of these known to data points, create a straight line, and it will estimate based on that straight line what the value of unknown y will be at that particular unknown x. Okay, so you can see here we are saying that we want to know it through all the range, and when that is the case, so this is all the range. When that is the case, you are going to get a straight line through every pair of every consecutive pair of known data point. Okay, so let me label these things. So this is our interpolated data, and this is our known data. And I have forgotten to close this string, and you'll see that this is the result. So if you compare this with our uh, nearest neighbor interpolation, so let me say that this is again a scatter. So if you compare these with this, you can easily check that this is a better estimation, right? So that's why, although this nearest neighbor interpolation method is very easy to implement, no one actually uses it for 1D data. For multidimensional data, due to its speed, sometimes depending on the problem, one might use it, but in 1D data, it is never the case. Okay, so as we saw for the nearest neighbor interpolation case also, this linear interpolation is better than that. And if you have more data, this becomes more accurate. Okay, so suppose our x3 is 0 to 6, and here we have point at the interval of say 0.25. Okay, and similarly y3 will be sine of x3, and we're going to plot them and pass them, and let me change this color to be something different. Unknowns. Okay, these are also gonna be 3. I can remove these 2 lines. They were unnecessary. And also, if you had to uncomment them at place, they will be where. Yeah. So here you can see, if I just don't plot it, don't plot our interpolated value, you will see that the our known data points are already very dense. And if we just join straight lines going through each of the consecutive pairs, we will have a very good approximation of our unknown data points. Okay, so let us do that. You will see that this is already looking like a perfect sine curve. So if I increase this, the density of unknown points more, you'll see that this is looking like a sine curve. So if I also stop plotting our known data, you'll see that how accurate this can be. So although This method is fairly simple. If your data is reasonably dense, not like this, you will get a wonderful approximation with this linear interpolation method. So let me print everything, and here let me give it some opacity. Yeah, okay. So let me quickly note, make a cell and note all of these things. So nearest neighbor interpolation is the simplest, but often ineffective. That means cannot provide good approximation in 1D data, but this is used for in multi-dimensional analysis for its speed. Linear interpolation is much better than nearest neighbor interpolation if your known data points are reasonably dense. You can get near accurate approximation through this method. Okay, so I hope you have understood the concept of this interpolation, and you can see how effective it can be to estimate the value of unknown data points based on your known data. Okay, so what we can do now is check this for multiple functions. So we have checked sine, let us check cos. You will see that this is again working. Let us check exponential. You will see that again here the approximation is quite good. Let me check a damped sine. So let's make it less damped. You can see that for all the cases, this is giving a very good approximation. So let us check for some polynomials also, say x3 to the power 3 minus 3x squared plus 2x minus 5. And we can use the broadcasting method here so that we don't forget putting dots. So here I forget to put a dot because this will be dot minus, this will be dot plus. So we can just use this at the rate dot macro. Okay, and here the problem is that this is like this. Okay, so here also you can see that this is giving a very good approximation. So that's the advantage of using linear interpolation. But if your data point is not that dense, then also in these cases you will see that this is reasonably good, but it can be better and it can be achieved. Some better results can be achieved with other interpolation methods, and we are going to learn about them next. One will be polynomial interpolation, and another will be spline interpolation. Okay, and here we will not be writing the functions from scratch. Rather, I will be using a package where these will be implemented. Okay, let us see how we can do that. So the name of the package is interpolations.jl. You can click it and it will redirect you to the page of GitHub page of this package. You can go to the documentation with this link, and here it is saying how to use this. So we first have to install this in our notebook. So let us do that. And while it is installing, let us briefly go through the documentation. Okay. So here you can check an example usage. So this xs is our known point, and this a is also our known point. Okay, so these two are known points, and here we can use this package like this. So we can create a linear interpolation object without extrapolation. So what extrapolation is, I will briefly touch up towards the end of this lecture, and will not be doing that in this course. Okay, but I will tell you what this is. So here we can use this function and pass it these two arguments, which are our known data points, and that will give you another function called interlinear. That's what the uh, nomenclature that we have used. And if you use this function with a positional argument 3, you will get exactly log 3 because this is one of the data points that was known to us. But if you give some unknown points, then it will give you an approximate value. So this is different than what we have seen. So we can check here. We can all this code. Let me comment it out for now. And let me print everything so that we can see both the result. The problem here is that this linear interpolation method is already defined as a function here. So we have defined this function, and this package is also providing this function. So both of them are apparently contradicting. So what we can do is we can rename our functions with custom name so that it will not be contradicting with the packages. Okay. So what we can do, we can call this nearest neighbor interpolation custom, and we can change it everywhere. Here also, and here also. And we can similarly make this linear interpolation custom, and we can change it here, here, here. Okay. So if I save the notebook now, everything should be running. Let me quickly check if I've missed something. So this was disabled. Okay, no issue. This was also disabled. No issue. These are working, and here also this is working. So it is not giving us the error anymore. Okay. So let me quickly change the variable names. So let's make it ys, and let us go through how to use this linear interpolation function from this interpolations.jl package step by step. Okay, so let us see how this is defined. So these are our known data, this x's and ys. So we are going to use this linear interpolation method that is defined inside this interpolations.jl package, and this takes two arguments. You can check the documentation here. So these nodes and a, these are our independent and dependent variables. Okay. So what this will return is a function. Here we have stored that function in the variable interplinear, and when you are calling that function with a value here 3 at 3.1, it will give us the result with estimation. So what will happen is that if you are asking for a value which is already in our known data, then it will give an exact result. So here 3 is in our known data, and if we ask what is the estimation of this data will be at x equal to 3, this will give us exactly the answer log 3. And when we are passing something unknown which is not in our known data set, then it will give you approximate result, and that approximation will be using the linear interpolation method that we have seen. So what we can do here now is, let me just copy this thing and paste it here. So we will use this linear interpolation method that is defined inside this interpolations.jl function, and also the function that we have written here. So not here, here. So and we will see that whether both of them are giving the exact same result. So what you can do is we can use this linear interpolation function, and that will take two arguments, x and y, and let me call them four unknowns, four, so that we don't run into other errors. Yeah, interpolated data from our function, and let's make the legend font size to be 6. Yeah, so it is pretty okay. Now here we have created this function. This is from the interpolations.jl package, and now we can get estimates for these unknown values using this function, and we can do that using y unknowns. So let us name the variable like this, and we can use it like this. So this is the name of the function. We will call it and we'll pass the array of unknown data points here. And you see this will give you, no, okay, this will not give you an error because this is defined for both arrays and single points. So this will work. You can also specify dot here, that will also give you same result. Okay. So what you can do is you can just skip this part and you can directly plot it. So this will be the same plot, only our estimated values will be obtained from this function, which was in turn obtained from this neural interpolation function defined in the package. And in the previous case, our estimation was obtained from the function that we wrote from scratch. Okay. So let me quickly change the color also and marker also. And you can see that these are overlapping. So what you can do is we can give some opacity, and you can probably see that both of these points are overlapped at the same position. Okay, so that proves that the function that we wrote is actually correct, and this is the same as the function that is defined inside this package. So if you do not want to write this whole function, you can just do it using this linear interpolation function defined inside this interpolations.jl package. The added benefit of using this package is that here you can do interpolation in 2 dimension also. So here we have not touched upon that, how to do 2D interpolations using this function. So that will be out of scope for this video. When you are using this function, you can also do 2D. So this is the GitHub page of that package, and this is the documentation of that package. You can check everything. So all the things that I've talked is given here. So probably a 2 dimensional example is also given. So you can check those. And if you have any questions, you can let me know. So now we're going to learn about this polynomial interpolation and spline interpolation. So we have come back to this presentation, and let me go to the polynomial interpolation case. Okay. So what this polynomial interpolation does is this estimates the unknown value by considering a n order polynomial function. So if you have collected n data points, then this will get the estimation from a n order polynomial. So this is very similar to do curve fitting. So for example, we saw one example where our function was x cubed minus x squared plus 3x minus 5. I think it was that. So we recently saw that example. So instead of doing linear interpolation, what this polynomial interpolation is going to do is it will assume a polynomial curve, and the coefficient of that curve will be chosen based on the points that we have obtained as our known points. Okay. So this is very similar to curve fitting. So we all know this fact that for n data points, there is exactly one polynomial of degree at most n minus 1 going through all of the n data points. So this is the fact that is being used to uniquely determine all of the coefficients of that polynomial. And these are, although for smaller data sets, can be used very efficiently. But if your known data set is large, the data itself need not be dense, but the range can be large. So the data that you have at your hand is effectively very large. In that case, this can become very time consuming. And this also suffers from some other artifacts. For example, this may exhibit oscillatory effects towards the boundary. And if you happen to choose a higher order polynomial than necessary, then you can also get unnecessary solutions. Okay. So for those reasons, this polynomial interpolation is also not used often, because a better option is available if you want to get similar results. So the main distinction between this linear interpolation and this polynomial interpolation is that for this case, the curve you are going to get will be smooth. And for the linear case, this will be continuous curve, but at the points, the derivative will be undefined because the slopes are different, right? So that's why this method exists, but it also has some drawbacks. But if you suppose you have some data and now you're trying to find minimum points or roots, in those cases, this polynomial interpolation can be used, and this gives very fruitful results. Okay, so in today's lecture, we'll not be seeing this interpolation method in action. Rather, we'll be going on to the next section where we'll learn about spline interpolation. So what spline interpolation is? This is exactly like polynomial interpolation, but instead of fitting the whole curve, we will be doing it piecewise. Okay. In that sense, this is similar to linear interpolation as well. So in linear interpolation, what we did was we obtained 2 points and then we fitted it using a straight line. Now here we'll be again getting those 2 points and we'll be fitting it using a polynomial curve. And in general, cubic spline is used. So our polynomial of degree 3 is used for this line interpolation, and that gives very accurate results. And it is also not computationally that much heavy. So here, what one can do is you can get some of the known points and you can fit polynomial through it, and you will have some options to match the slope at the intermediate points. So that is the way that you can get a smooth curve throughout a known range. So we'll use this line interpolation in action. So this is, again, I want to remember that this is like piecewise polynomial. Okay. So the polynomial interpolation and spline interpolation both will give you smooth estimation curve. So if you are probing the whole range of the dataset, in both cases, you will be getting a smooth curve, but polynomial interpolation can be very computationally heavy for large datasets, but spline is comparatively faster. And polynomial will try to fit all the points. And spline, what this will do, this will fit piecewise. So you don't need to worry about the size of your data because this will anyway be doing this piecewise. Okay. So we can obtain similar result, a smooth curve, and good approximation just with the polynomial of degree 3 or 5. So that is the advantage of using spline, and This is the method that is used most after linear interpolation. So we are going to see how we can use this using the package that we have installed here. So let me create a code block. So let me just remove all of these things. These are not necessary. Okay. This is like polynomial interpolation, but piecewise fitting is perfect. And this will give you smooth curves. So if your data is, yeah, so if your data is dense, then you will see that spline interpolation and your linear interpolation both are giving you very similar results. So what we can do is we will see one example of spline interpolation for one of the functions, may I say sine function that we have been using throughout the lecture. And then we will see some complicated functions and we will see the results of linear interpolation and spline interpolation side by side. That will give us an idea of what to use in what which cases. Okay. So this will be slightly time consuming. So this is computationally more expensive than linear interpolations. Okay. So let us again use this. So let me just copy this and paste it here. And what I will do is I will remove it. And this will just give us a plot. So again, like the linear interpolation function from the interpolations or GL package, we will also use the spline interpolation like this. So we will use this spline interpolation function. You can check the, sorry, this is cubic spline interpolation, and you can check the documentation. This is cubic spline because the piecewise polynomial will be cubic in nature. So here I will pass the known data and this will return a function. So let's call spline entropy. And if you want to get estimation, then what we will do is we will use this function that has been returned, spline entropy, and pass it a value at say 1.5. So it will take some time to run, and this is our estimation. So let us do one thing. Let us plot for say 0 to 0.1 from so 0 to 6 at the intervals of 0.1, and let us estimate using this spline interview function that is generated after we have used UV spline interpolation function on our known data. So let us run it, and you will see this is the result. So If this is unclear, the orange circles are our estimated values. So we can say that this is the interpolated values, and we can change the marker to be a star and the marker size a bit smaller. And you will see that this is matching a sine curve perfectly. We can also check that with this. So let me plot a faded gray line representing the exact sine curve. And you will see that our interpolated value is very closely matching the original sine curve. So you can compare this linear interpolation and this method, and I don't have to explain you guys, and you can see for yourself that this one is far superior when you're dealing with smoother functions. Okay, so that's how you can use cubic spline interpolation. So let me just say that this is the actual curve. Okay, so we have learned about interpolation in this video. So I would like to end today's video with a side-by-side montage of this linear and spline interpolation for various functions and various data sets with different densities, different ranges, those things, so that you can get a visual idea of what the estimation will look like for each case and which one to use depending on your situation. Okay, so I think we are already over 2 hours, so I will not take much more time. We'll just briefly see these examples, and after that, I will summarize today's class, say here, like we did in all other classes, and we'll also see what we can do in the next class. Okay, so let's see these examples quickly. So let me just do everything inside this begin and end block. Okay, so xk, let it be our known data point. So let it go from 0 to 10 at interval of say 0.5. And yk, it can be our function. So let us start with the exponential function. Okay, so we'll use linear as well as cubic spline. We'll plot them and we'll show the results side by side. We have seen how to do that when we were talking about data visualization, right? So let me, all of the codes we have explained and learned. So I will not do much talking while I'm typing the code. So just bear with me when I'm doing this. and say we want to get values in this range only, and our spacing will be much smaller. So let me just quickly run it. Something is wrong. So this should be xk, and this should be L into p1. And we need a new plot. And this should be till 10, and this should be our data, and this should be our linear estimation. And I have forgotten to give the x value here. This should come there. And you can see, so let's make it a line plot only. And you can see that this is the result of linear interpolation. So here we have our, with blue markers, we have our known data, and this orange line is our estimation. And see, this linear interpolation is giving a pretty good result. Let us do that for spline also. So let me quickly copy paste most of the thing. So we should be UV spline, and let us call this is entropy 1. Let me call it plot B. This is again root. This will be spline. This will be plot B, and this will be S. And what I will do is I will plot everything like this in a layout of 1, 2. And okay, so actually this will not be in an array. So that should fix the error. Yeah. So you can see that this is our linear interpolation and this is our spline interpolation. So let's do one thing here. Let's make the size of this plot a bit larger. So it was earlier 400 by 300. So let's make it 800 by 300. And also let us change the color to green for our spline interpolation so that we can see all of them differently. And while we're at it, let's also make the line width a bit larger. Okay, so you can see that both of them are giving almost accurate result, but here the discontinuity at the known points can be visibly seen, but here this is a smooth curve. So we can do another thing. We can actually plot both of them together and also plot it at the side. So let's make it a bit larger, 1000. And what is the issue here? Okay, so actually we are plotting three plots, but our layout is 1 cos 2. We want to make it 1 cos 3. And you will see that everything is plotted here. And you can see on the consolidated plot that everything is plotting on top of one another. And if we zoom it, then you will see that both results are almost matching, where the data points are very dense, but when they are a bit further, there you will see that this slight mismatch can happen. So now let us see this for all other some other functions. So what I will do for the next examples is that I will just plot this third plot, okay, so that we can see them on top of one another. So this should be this. Uh, yeah, so this is correct. Let me do one thing. Just change the variables so that it doesn't give any error. We also don't need plot C. So this is the plot. So suppose we want to now estimate the cost function. So let us run it. Okay, so sorry, this should be xk2 yk2 here also, and here also. Okay, so here you can see that the orange one is our linear interpolation and the green one is again our spline interpolation. So let's make it be transparent so that you can see both plots, and you can see here that the orange one has these discontinuities in slope like here, but the green one is always smooth. This will be even more visible when this will be more visible when your data points are less dense. So here you can see that although these known points are falling on both of the curves here, and you'll see this linear interpolation is giving us this kind of estimation where this is completely mismatching at these positions. Okay, but the spline interpolation is giving us a smooth estimation, although towards the edge you will see that this is deviating from the original curve. So we can check that also. So you can see that towards the edge the spline interpolation is also deviating from the original curve, although towards this region, this is very accurately matching with the cost function. Okay, so that's another example, and you can again check that when our data points are very close, both of them will give you near accurate estimation. So let us check for 0.25, and you see that here also all of the curves are falling on top of one another. So our estimation is actually very accurate. So let me check another example and then I will stop today's class. So let us look at the same range, but let's say our function is now a damped sine. So this will be sine times exponential minus say 0.5 times xk3, and if we plot it, you will see that this is our curve. So we can do one thing, we can make the points less dense, and we can also change this function. And what happened? Let me check. So let me do an anonymous function. Still not working. Okay, so it has worked. So I had to enclose everything in a parenthesis. And you can also see here that, so let me decrease the line with it. So you can also see here that this is our data, and this orange one is our linear interpolation, and the green one is our spline interpolation. And you'll see that when we have our data very densely spaced, all of them are matching with the actual curve. And when the data are far away, then you will see that the spline is giving more accurate result. So with that, I will like to end today's class. So I hope you have learned about interpolations a lot. And in the next class, we will be tackling differentiations. So let me quickly tabulate what we have learned in today's class. So we learned what numerical computation is, different types of numerical computations, interpolations, and different kinds of them. We did some interpolation from scratch. We also checked a package interpolations.jl, which is more capable, and we learned that linear interpolation can provide good estimation. Spline interpolation is better if the density of known points is more, then both will give near accurate results. So that's today's learning. And in the next class, we're going to learn about numerical differentiations. Okay. So thanks everyone for sticking to the end of this lecture, and I hope you have enjoyed this lecture a lot because this was the main goal of our course to learn Julia so that we can do numerical computation, and we started that in today's lecture, and we'll be continuing this in the next two lectures also. So in today, we learned the very basics, and the first numerical computation that we did is estimating some unknown values from known data points, and we have seen different ways to do it. Okay, thank you everyone for joining the class, and I will see you in the next video.